Okay, in our previous video, we discussed what I call the mother of all thermodynamics equations. The Gibbs free energy, or the change in that, I should say, is calculated by taking the change in enthalpy minus this term T times delta S, which is T times the change in the entropy. And essentially what Gibbs had realized, and what they realized this number was useful. If this number comes up positive, that means the free energy of the system is trying to increase, and they just don't do it spontaneously. If it's negative, though, the process can go forward. This involves, as you can tell, both delta H and delta S, and they can both be favorable, and the thing is going to go for sure. They can both be unfavorable, and there's no way the thing will occur spontaneously at that temperature. And then they can be fighting each other, and that's where this equation usually is most useful in predicting whether it'll go or not. I want to do a mathematical calculation or two now for you, just to show you some of the things that can be done, and talk a little bit about products minus reactants kind of thing that we can do with most of these thermodynamic things and why we can. So on page 364 in your book, they have an equation of fermentation, actually, of glucose becoming alcohol and carbon dioxide. So the equation here is C6H12O6, which is a simple sugar glucose, and we're getting C2H5OH, which is ethyl alcohol, and we're getting, I believe it's 2 moles, I think, in the balanced equation there. Yeah, that get produced. Actually, it's 2 of each of these products. I should have thought of that. We need to have 6 total carbons there. So anyway, there are some numbers given for simply delta H and delta S at different temperatures, and just asked to find delta G. So it's a pretty simple mathematical thing. What we're trying to figure out is this process spontaneous under the given conditions? Will it occur spontaneously? So the information here, it reads this way. Given that the changes in enthalpy and entropy are negative 139 kilojoules, notice the unit, and 277 joules per Kelvin, that would have to be the entropy number, notice it's in joules, respectively, so they're saying in the order of enthalpy and entropy. For this reaction, calculate the change in the Gibbs energy at 25 degrees C. And this is like yeast or something fermenting sugar and making alcohol. Don't let the government catch you doing this unauthorized. So we just are going to have to plug in here, and I like to do this way on the units, okay? I'm trying to find delta G. The delta H that was given in kilojoules. I will often leave it that way. It's a negative 139 kilojoules minus, now I got to be careful here, T has got to be in Kelvin. And now I have this energy for the, or the number for the entropy given as 277 joules per Kelvin. Notice how I put it in as 0.277 kilojoules per Kelvin. I divided it by 1,000 to put it into kilojoules. Now if you think about that, look at what the units would do. Kelvins would cancel kelvins, and I would be left with kilojoules. The only way in the world that I can then subtract these two numbers that I'll have here by the time I multiply by 298, the only way I can subtract them is if they're in the same units. And if I don't fix either one of the units, it really doesn't matter. But this is going to give me a free energy change, or a Gibbs energy change, in kilojoules, because I chose to put everything in kilojoules. So you go ahead and you take the negative 139, you multiply the 298 by 0.277, and you get 83. So negative 139 kilojoules minus 83 kilojoules, because that is a positive number there, and you get a final answer for this of a negative 222 kilojoules. So it's kind of a simple calculation, but here's what it means. When this process occurs of this yeast being fermented to alcohol, The free energy change within that system is negative 222 kilojoules per every mole of sugar. Yep, that's what it's based on. So it should happen spontaneously. Now, to rehash what we did earlier real quick, I didn't need to do the math to prove that part. Because if you look at the delta H number, it is negative. According to the universe, giving off energy is favored. Going to less available energy in the system is favored. Also, you'll notice something else. The entropy change over here was a positive number. And according to the second law of thermodynamics, an increase in the randomness or disorder is favored. So both of the thermodynamic quantities were in what we call sort of a favorable condition. So this is an always. There's no question that this is going to come up a negative and indicate that it is spontaneous. Now, if we want to know the amount, it's good to go ahead and do the math. But in this case, it was not totally necessary for me to do the math in order to answer the question, is it spontaneous or not? Okay, well, we've got one other little thing here that I need to talk about real quick, and that is a state function. And I want to go ahead and talk about this real fast. It's a function. It's something that doesn't depend on the path, but just on being where you're at. For example, if I put a thing at a higher gravitational potential energy, it really doesn't matter if I took it around the room, stood it on its ear, and then ended up at whatever height above the floor. That just depends on how high I'm above the zero potential place, if that's the floor. It doesn't matter how I got there at all. And this is a huge thing. And one of the biggest concepts that we're going to look at here involves things like standard values. Standard enthalpy of formation is a big one that I'll get into. I'm going to come back to it in a minute. But a lot of thermodynamic calculations are carried out based on standard conditions. Like if gases are at 1 atmosphere, solids and liquids are pure, aqueous solutions are 1 mole of solute per liter, which is that 1 molar number. And usually it's at 298 K is the temperature, 25 degrees C. And the bottom line is that under those conditions, there is a certain change that happens in going from point A to point B. And it doesn't matter how you got there at all. And I'm going to come back to that in a minute. I want to show you a way that this plays out in an example problem from your text in this same section. It's on page 361. And then I'm going to come back and deal a bit more with this concept of a state function. Let me drag this up just a hair. We'll focus first on this problem right here. This is the example problem. It's on 361. This is, the half mole is in this just so you can see where it comes in. This could have been 1 mole, but what we have here is a half a mole of hydrogen gas and a half a mole of carbon dioxide forming a half a mole of water vapor right here and a half a mole of carbon monoxide. This is related to a reaction called the water gas shift that actually we usually want to go the other way. But they want to know about the entropy change that happens here, like calculate it. Well, if you look at this, it's a tough call because I have a half a mole of gas and a half a mole of a different gas, and they are each making 2 new gases, a half a mole each. So you can't eyeball this one and say, oh, it looks like the entropy is getting more disorganized or less. But there are things called standard entropies at different temperatures. And the delta S for this reaction doesn't really matter. The change of entropy doesn't really matter how you got from point A to point B. It just matters that you got there. So this symbol right here is a mathematical symbol that means the sum of. And so what this is basically saying is this: add up all the standard entropy, add up the numbers for the entropy that are in your products. Also do the same, sum up or add up all of the entropy, and this symbol here means the same, sum up all the entropy of all of your reactants and subtract them, and whatever the difference in the entropy is, because they are state functions, you're going to have the change that took place, and it doesn't matter how the change happened as long as you got from point A to point B. So in the book, they give tables for this. The 188.7 joules per Kelvin per mole that you see in this, if you look that up, that is the standard entropy of water. As a matter of fact, let's see, water vapor is on page 360. There's a little chart on the left side, and it gives that value. So there's a half a mole involved. Notice how moles canceled here. So this part right here, this whole bit above that is H2O calculation. I also need to do another product, and that is carbon monoxide. There's a half a mole of it. Its value is 197.6 joules per degree per mole. So when I cancel out the moles, I'm going to end up with just joules per Kelvin on that. Over here on this side, I'm going to sum up, it's always products minus reactants. So these ones over here, this is going to be for the reactants. If you look it up, the 130 number is the standard entropy for H2, and it's also a half a mole, so that's why we're multiplying by that. It's not always the same number on coefficients, but in this case it is. And then the only other thing is CO2. If you look in the table, you're going to find that 213 value right there is for CO2. So you take a half times the number, a half times the other number, add them together, and you get a grand total, and you do the same thing for all your reactants and your products, and you subtract them, and if you check page 361 in the book, this example problem is there, it comes up 20.9 joules per Kelvin, and it's a positive number. So what that basically tells you is that this was a positive delta S. That means that even though it was tough to call by eyeballing it, it appears there was a very slight entropy increase in this particular reaction. So we would expect this to be favored in thermodynamic calculations. While I've got this screen up here, I'm going to show you one more. It's off of page 367 in your textbook, and it's shown here in black. This is a couple of NOs and an oxygen. So let me jot the reaction in here. It's two NOs and an O2 making a couple of NO2s. If you check on page 367, you will find this is problem 7 in your book. They give you several standard entropies for these different substances, and they want to know the entropy change. Well, you'll notice that it's got to be products minus reactants, and I kind of goofed, there's a 2 right there. So the 2 times the 240 on that screen is for the NO2, that's the only product. So notice we're multiplying by 2 moles here, because that's what the coefficient is. Minus, and then we got that big bracket that's got 1 times the 205 and 2 times a 210. And I believe the 210 number, just looking here to make sure, yeah, that's for the NO. The oxygen is the 205 number. Those are your reactants. So you do all your math and sum up those 2 brackets, and this one has a negative entropy change. So the reason is we went from like 2 gases, here's a gas and here's a gas, and we made fewer molecules of gas. We had 3 molecules of gas total, a couple NOs and an O2, and now we only have a couple of NO2s. So it would make sense that that's not as random, and that's why this came up a negative number for delta S, for the entropy change. So if I can do it quickly, and I don't know if I can, to go back here and look at this definition, and then I'll come back and do one more video to wrap this up. But if you have something under standard conditions and you make a mole of it, there's this definition here that the delta HF0, where the little f means heat of formation, where before we had like heat of solution. This is still a heat change, but it's a different kind. And the little 0 means being at standard conditions. It's this heat of formation is the enthalpy change to make 1 mole of the substance from its elements in the standard state. And so kind of as a result of this definition, the heat of formation for any element is 0. So we'll come back to this